OSI model. In this video, we are going to learn about OSI model. The International Organization for Standardization developed the Open System Interconnection, that is OSI reference model. OSI model is the most widely used model for networking. OSI is a 7-layer standard. The OSI model does not specify the communication standard or protocols to be used to perform networking tasks. Services provided by OSI model provides peer-to-peer logical services with layer physical implementation. Provides standards for communication between systems. Defines point of interconnection for the exchange of information between systems. Each layer should perform a well-defined function. Physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer. The OSI model does not specify the communication standard or protocols to be used to perform networking tasks. OSI model layers. In this video, we are going to learn about layers of OSI model. OSI layers basically consist of 7 layers as follows. Physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer. Physical layer. It is the lowest layer of the OSI model. This layer transmits raw bits over a communication channel. The design issue of physical layer considers 4 factors: electrical, mechanical, procedural attributes, function attributes. The electrical attributes describe the voltage level or current level. The mechanical attributes describe the connectors and the wires of the interface. The procedural attributes describes what connectors must do and the sequence of events required to effect actual data transfer across the interface. The functional attributes describe the function to be performed by the physical interface. Data link layer. It is responsible for the transfer of data over the channel. It groups zeros and ones into frames. A frame is a series of bits that forms a unit of data. DLL detects and corrects the transmission errors using error correction method. It also provides data flow control to ensure that the DTE does not become overburdened. It identifies the devices on the network. Network layer. It specifies the intra-network operations and different types of addressing and routing services. Logical and service addressing are provided from network layer. It also provides switching control and terminal connections. The X25 specification is included in this layer. Transport layer. It is responsible for reliable end-to-end data transfer. Hence, the optimum utilization of network resources occurs. The transport layer performs the service of sending and receiving segments of data to session layer. It also provides flow control, sequence numbering, and message acknowledgement. Session layer. It adds mechanisms to establish, maintain, synchronize, and manage communication between network entities. This layer has specific services, primitives, and protocol data unit which are defined in ISO. Presentation layer. It is responsible for data compression, data expansion, data encryption, and data decryption. It accepts data types int, char, etc. from application layer and then negotiate with its peer layer as to the syntax representation. Application layer. It supports end-user functions like login, password, and file transfer. This layer contains service elements to support application processes such as job management, financial data exchange, and business data exchange. This layer also supports virtual terminal and virtual file concepts. OSI layers with functions. In this video, we are going to see about OSI layers with functions. Open System Interconnection (OSI model), a suggested standard for communication that was developed by the International Organization for Standardization (ISO). Physical layer. Media, signal, and binary transmission. It is concerned with transmission of unstructured bit stream over physical medium. It deals with the mechanical, electrical, functional, and procedural characteristics to access physical medium. Data link layer, MAC and LLC physical addressing. It provides reliable transfer of information across the physical link. It sends blocks, that is frames, with necessary synchronization, error control, and flow control. Network layer, path determination and IP, logical addressing. It provides upper layers with independence from the data transmission and switching technologies used to connect systems. It is responsible for establishing, maintaining, and terminating connections. Transport layer, end-to-end connections and reliability. It provides reliable, transparent transfer of data between endpoints. It provides end-to-end error recovery and flow control. Session layer, inter-host communication. It provides a control structure for communication between applications. It establishes, manages, and terminates connections between cooperating applications. Presentation layer, data representation and encryption. It provides independence to application processes from difference in data representation, that is syntax. Application layer, maximum transfer unit (MTU). In this video, we are going to see about maximum transfer unit (MTU). MTU Maximum Transfer Unit defines the largest data packet size that can be transmitted as one network. Any messages larger than the MTU are divided into smaller packets before being sent. In order to transmit the most amount of data in single transmission, we should set the MTU to a high value such as 1468. If the MTU is low, then it will take more number of packets to transmit the same amount of data, compound to that with a higher valued MTU. Because each packet has a fixed header size and requires an acknowledgement response before the next packet can be sent, sending more packets for the same amount of data can be slower and waste a lot of bandwidth. If MTU is too high, then the router will try to send packets larger than the network can handle, resulting in packet fragmentation, where we are forced to split the packets when they reach our network and can cause problems with some websites, that is, mainly ones using HTTPS and applications. The maximum MTU size over the Ethernet is 1500 bytes, and the router should be configured to as close to this as it will be accepted. Internet Protocol IP. In this video, we are going to see about Internet Protocol IP. The Internet Protocol IP is the primary network protocol by which data is sent from one computer to another on the Internet. Each computer, known as a host, on the Internet has at least one IP address that uniquely identifies it from all other computers on the Internet. The functions of Internet Protocol include defining the Internet addressing schemes, moving data between the network access layer and host-to-host transport layer, performing fragmentation and reassembly of datagrams, routing datagrams to remote hosts. There are currently two versions in Internet Protocol, IPv4 and IPv6. Overview of Internet Protocol version 4. Internet Protocol version 4, that is IPv4, is the fourth version of the IP and a widely used protocol in data communication over different kinds of networks. IPv4 is a connection-less protocol used in packet-switched layer networks such as Ethernet. It provides a logical connection between network devices by providing identification for each device. Internet Protocol version 4 standard that features IP addresses 4 bytes, that is 32 bits in length. IPv4 uses 4 1-byte decimal numbers separated by a dot, that is 192.168.1.1. There are many ways to configure IPv4 with all kinds of devices, including manual and automatic configurations depending on the network type. Overview of Internet Protocol version 6. The Internet Protocol version 6 IPv6 is more advanced and has better features compared to IPv4. It has the capability to provide an infinite number of addresses. IPv6 is replacing IPv4 to accommodate a growing number of networks worldwide and help solve the IP address problems. The newer Internet Protocol version 6 IPv6 standard features addresses 16 bytes, that is 128 bits in length. IPv6 uses hexadecimal numbers that are separated by colons, that is FE80 : D4A8 : 6435 : D2D8 : D9F3B11. IPv4, IPv6. IPv4 address are 32 bits in length. IPv6 address are 128 bits in length. IPv4 address are binary numbers represented in decimals. IPv6 addresses are binary numbers represented in hexadecimals. IPsec supports is only optional. Inbuilt IPsec supports. Fragmentation is done by sender and forwarding routers. Fragmentation is done only by sender. No packets flow identification. Packet flow identification is available within the IPv6 header using the flow label field. Checksum field is available in IPv4 header. No checksum field is in IPv6 header. Options fields are available in IPv4 header. No options fields but IPv6 extension headers are available. Address Resolution Protocol ARP is available to map IPv4 address to MAC address. Address Resolution Protocol ARP is replaced with a function of Neighbor Discovery Protocol NDP. Internet Group Management Protocol IGMP is used to manage multicast group membership. IGMP is replaced with Multicast Listener Discovery MLD messages. Broadcast messages are available. Broadcast messages are not available. Instead, a link local scope all nodes multicast IPv6 address, that is FF02 is equal to 1, is used for broadcast similar functionality. Manual configuration static of IPv4 addresses or DHCP dynamic configuration is required to configure IPv4 addresses. Auto configuration of addresses is available. Transmission Control Protocol TCP. In this video, we are going to see about Transmission Control Protocol TCP. The second transport layer is protocols TCP. TCP, Transmission Control Protocol, is a protocol that works with the Internet Protocol IP to send packets of data between computers over the Internet. TCP establishes a full duplex virtual connection between two endpoints. Each endpoint is defined by an IP address and a TCP port number. The operation of TCP is implemented as a finite state mission. TCP IP protocols are modeled in 4 layers. TCP operation. The primary purpose of the TCP is to provide reliable, securable logical circuit or connection service between pairs of processes. To provide this service, Internet Communication System requires facilities in the following areas: basic data transfer, reliability, flow control, multiplexing, connections. Basic data transfer. TCP is able to both transmit and receive data streams simultaneously, even though this is opposite to the basic concept of data transmission in many underlying network technologies. The TCP is able to transfer a continuous stream of data in each direction between its users by packaging some number of data into segments for transmission through the Internet system. In general, the TCPs decide when to block and forward data at their own convenience. The data unit transmitted from TCP layer is referred to as a segment. The size of the segments and the timing at which they are sent is generally left to the TCP module. TCP applications request that the data is pushed by instructing the TCP module to deliver all data up to that point without maximum transmission unit (MTU). Reliability. TCP assigns a sequence number to each byte transmitted and expects a positive acknowledgement ACK from the receiving TCP. If the ACK is not received within the timeout interval, the data is then retransmitted. The receiving TCP uses the sequence numbers to rearrange the segments when they arrive out of order and to eliminate duplicate segments. TCP provides reliable communication through a positive acknowledgement system. Flow control. TCP provides a means for the receiver to govern the amount of data sent by the sender. This is achieved by returning a window with every ACK indicating a range of acceptable sequence numbers beyond the last segment successfully received. The window indicates an allowed number of octets that the sender may transmit before receiving further permission. Multiplexing. TCP is able to provide a connection-oriented environment for many simultaneous processes within a single host. TCP uses a set of ports which, when concatenated with the IP address of the host, providing a socket that uniquely identifies an application process anywhere within the Internet. Connections. The reliability and flow control mechanisms described above require that TCPs initialize and maintain certain status information for each data stream. The combination of this information, including sockets, sequence numbers, and window sizes, is called a connection. Each connection is uniquely specified by a pair of sockets identifying its two sides. When two processes wish to communicate, their TCP must first establish a connection, initialize status information on both sides. When the communication is complete, the connection is terminated or closed to free the resources for other users. TCP header. The TCP segment comprises of a header and a variable length data area that ultimately carries application data. TCP header at minimum is 20 bytes long and maximum 60 bytes. Source port 16 bits identifies source port of the application process on the sending device. Destination port 16 bits identifies a destination port of the application process on the receiving device. Sequence number 32 bits. Sequence number of data bytes of a segment in a session. Acknowledgement number 32 bits. When ACK flag is set, this number contains the next sequence number of the data byte expect and works as acknowledgement of the previous data received. Data offset 4 bits. This field contains two meanings. First, it tells the size of TCP header 32-bit words. Secondly, it indicates the offset of data in current packet in the whole TCP segment. Reserved 3 bits. Reserved for future use and all are set 0 by default. Flags 1 bit each. NS nonce some bit is used by explicit congestion notification signaling process. CWR. When a host receives packet with ECE bit set, it sets congestion windows reduced to acknowledge that ECE received. ECE has two meanings. If SYN bit is clear to 0, then ECE means that the packet has its CE, that is congestion experience, bit set. If SYN bit is set to 1, ECE means that the device is ECT capable. URG indicates that urgent pointer field has significant data and should be processed. ACK indicates that acknowledgement field has significance. If ACK is clear to 0, it indicates that packet does not contain any acknowledgement. PSH, when set, it is a request to the receiving station to push data as soon as it comes to the receiving application without buffering it. RST, reset flag, has many features. It is used to refuse an incoming connection. It is used to reject a segment. It is used to restart a connection. SEN. This flag is used to set up a connection between hosts. FIN. This flag is used to release a connection and no more data is exchanged thereafter. Because packets with SYN and FIN flags have sequence numbers, they are processed in correct order. TCP ClientServer Model. TCP is a peer-to-peer connection-oriented protocol. There are no master or subordinate relationships. The applications, however, typically use a client-server model for communications. A server is an application that offers a service to Internet users. A client is a requester of a service. An application consists of both a server and a client part, which can run on the same or on different systems. Users invoke the client part of the application, which builds a request for a particular service and sends it to the server part of the application using TCP IP as a transport medium. The server is a program that receives a request, performs the required service, and sends back the results in a reply. User Datagram Protocol. In this video, we are going to see about User Datagram Protocol. UDP is another transport protocol in the TCP IP suite. User Datagram Protocol is an Open Systems Interconnection (OSI) transport layer protocol for client-server network applications. The service provided by UDP is an unreliable service that provides no guarantees for delivery and no protection from duplication. The simplicity of UDP reduces the overhead from using the protocol, and the services may be adequate in many cases. UDP is widely used in video conferencing and real-time computer games. The protocol permits individual packets to be dropped and UDP packets to be received in a different order than that in which they were sent, allowing for better performance. UDP header format. An UDP datagram header contains 4 fields of 2 bytes each. Source port number, destination port number, datagram size, checksum. Source port number. UDP 16-bit packets from a client use the source port as a service access point (SAP) to indicate the session on the local client that originated the packet. UDP packets from a server carry the server SAP in this field. Destination port number. UDP packets from a client use this as a service access point (SAP) to indicate the service required from the remote server. Datagram size. The length field specifies the length of the whole packet in octets, including header and data portions. The shortest possible packet can be 8 octets long. Checksum. An optional 16-bit checksum computed over the entire UDP datagram plus a special pseudo-header of fields. Internet Control Message Protocol (ICMP). In this video, we are going to see about Internet Control Message Protocol (ICMP). The ICMP is an extension to the Internet Protocol which is used to communicate between a gateway and a source host to manage errors and generate control messages. The Internet Protocol (IP) is not designed to be absolutely reliable. The purpose of control messages (ICMP) is to provide feedback about problems in the communication environment, not to make IP reliable. There are still no guarantees that a datagram will be delivered or a control message will be returned. Some datagrams may still be undelivered without any reports of their loss. The higher-level protocols that use TCP IP must implement their own reliability procedures if reliable communication is required. IP is an unreliable protocol that has no mechanisms for error checking or error control. ICMP was designed to compensate for this deficiency. However, ICMP does not correct errors, simply reports them. ICMP uses the source IP address to send the error message to the source of the datagram. ICMP messages consist of error reporting messages and query messages. The error reporting messages report problems that a router or a destination host may encounter when it processes an IP packet. In addition to error reporting, ICMP can diagnose some network problems through the query messages. The query messages in pairs give a host or a network manager specific information from a router or another host. Types. There are two classes of ICMP messages. Error messages have a type from 0 to 127. Informational messages have a type from 128 to 255. Code varies according to the message type. Checksum used to detect data corruption in the ICMP message and parts of the IPv4 header. Body of message varies according to the message type. Address Resolution Protocol (ARP). In this video, we are going to see about Address Resolution Protocol (ARP). ARP is a protocol used for mapping an IP address to a computer connected to the local network LAN. Since each computer has a unique physical address called a MAC address, ARP converts the IP address to the MAC address. This ensures that each computer has a unique network identity. ARP message format. Following fields are the Address Resolution Protocol ARP message format. Hardware type. Hardware type field in the Address Resolution Protocol ARP message specifies the type of hardware used for the local network transmitting the Address Resolution Protocol ARP message. Ethernet is the common hardware type and the value for Ethernet is 1. The size of this field is 2 bytes. Protocol type. Each protocol is assigned a number used in this field. IPv4 is 2048, that is 0x0800 in hexa. Hardware address length. Hardware address length in the Address Resolution Protocol, that is ARP message, is length in bytes of a hardware MAC address. Ethernet MAC addresses are 6 bytes long. Protocol address length. Length in bytes of a logical address, that is IPv4 address. IPv4 addresses are 4 bytes long. Opcode. Opcode field in the Address Resolution Protocol ARP message specifies the nature of the ARP message. 1 for ARP request and 2 for ARP reply. Sender hardware address. Layer 2, that is MAC address, address of the device sending the message. Sender protocol address. The protocol address, that is IPv4 address of the device sending the message. Target hardware address. Layer 2, that is MAC address of the intended receiver. This field is ignored in requests. Target protocol address. The protocol address, IPv4 address of the intended receiver. Working of Address Resolution Protocol ARP. Step 1. When a source device wants to communicate with another device, source device checks its Address Resolution Protocol ARP cache to find it already has resolved MAC address of the destination device. If it is there, it will use that MAC address for communication. To view the Local Address Resolution Protocol ARP cache, open Command Prompt and type ARP-A without double quotes using Windows operating systems. Step 2. If ARP resolution is not there in local cache, the source machine will generate an Address Resolution Protocol ARP request message. It puts its own data link layer address as the sender hardware address and its own IPv4 address as the sender protocol address. The target hardware address will be left blank since the machine is trying to find that. Step 3. The source broadcasts the Address Resolution Protocol ARP request message to the local network. Step 4. The message is received by each device on the LAN since it is a broadcast. Each device compares the target protocol address, that is IPv4 address of the machine to which the source is trying to communicate, with its own protocol address, that is IPv4 address. Step 5. When the targeted device checks the target protocol address, it will find a match and will generate an Address Resolution Protocol ARP reply message. It takes the sender hardware address and the sender protocol address fields from the Address Resolution Protocol ARP request message and uses these values for the targeted hardware address and targeted protocol address of the reply message. Step 6. The destination device will then update its Address Resolution Protocol ARP cache since it needs to contact the sender machine soon. Step 7. Destination device send the Address Resolution Protocol ARP reply message, and it will not be a broadcast but a unicast. Step 8. The source machine will process the Address Resolution Protocol ARP reply from destination. It stores the sender hardware address as the layer 2 address of the destination. Step 9. The source machine will update its Address Resolution Protocol ARP cache with the sender hardware address and sender protocol address it received from the Address Resolution Protocol ARP reply message. Proxy ARP. Proxy ARP is a method that allows hosts on different LANs to successfully transmit packets across an internetworking environment. Reverse Address Resolution Protocol RARP. In this video, we are going to see about Reverse Address Resolution Protocol RARP. Reverse Address Resolution Protocol is a protocol using which a physical machine in a LAN could request to find its IP address from the ARP table or cache from a gateway server. When a system with a local disk is bootstrapped, it normally obtains its IP address from a configuration file that is read from a disk file. But a system without a disk, such as an X terminal or a diskless workstation, needs some other way to obtain its IP address. The principle of RARP is for the diskless workstation to read its unique hardware address from the interface card and send an RARP request, that is, an RARP request broadcast in a frame over the network asking for someone to reply with diskless system's IP address, that is, in an RARP reply. The format of an RARP request is identical to an ARP, that is, Address Resolution Protocol request. An RARP server attached to the physical network normally provides the mapping from a hardware address to an IP address for many hosts, that is, diskless systems on the network. The mapping is contained in a disk file, that is, normally /etc/ethers on Unix systems. The reply from the server is unicast, that is, to the sender of the RARP request. As with ARP requests, RARP requests are sent as hardware, that is, Ethernet level broadcasts. This means they are not forwarded by routers. Thus, the server must be present on the same physical network as the diskless workstation. To allow diskless stations to bootstrap even when the main RARP server is down, multiple RARP servers are provided on a single network. As the number of servers increases, the network traffic increases since every server sends an RARP reply to every RARP request. The diskless system normally uses the first RARP reply that it receives. Furthermore, there is a chance that each RARP server can try to respond at about the same time, increasing the probability of collisions on an Ethernet. That is, this is not a problem with ARP because only a single host sends an ARP reply. Domain Name System (DNS). In this video, we are going to see about Domain Name System (DNS). DNS is an abbreviation for Domain Name System, a system for naming computers and network services that is organized into a hierarchy of domains. DNS naming is used in TCP IP networks such as the Internet to locate computers and services through user-friendly names. When the user enters a DNS name in an application, DNS services can resolve the name to other information associated with the name such as an IP address. For example, most users prefer a friendly name such as example.microsoft.com to locate a computer such as a mail or web server on a network. A friendly name can be easier to learn and remember. However, computers communicate over a network by using numeric addresses. To make the use of network resources easier, name systems such as DNS provide a way to map the user-friendly name for a computer or service to its numeric address. In this example, a client computer queries a DNS server asking for the IP address of a computer configured to use host 8 example Microsoft.com as its DNS domain name. Because the DNS server is able to answer the query based on its local database, it replies with an answer containing the requested information, which is the host A resource record that contains the IP address information for host 8 example Microsoft.com. Ping, that is Packet Internet Groper. In this video, we are going to see about ping, that is Packet Internet Groper. Pinging is one of the easiest ways to test connectivity across the network and confirm that an IP address is reachable. The DOS ping utility, that is ping.exe, uses ICMP to forward an echo request packet to the destination address. The destination then responds with an ICMP echo response packet. Although the test seems trivial at first sight, it is a powerful diagnostic tool and can demonstrate correct operation between the internet layers of two hosts across a WAN regardless of the distance and number of intermediate routers involved. The ping utility can only ping an IP address. This is due to the fact that the ICMP messages are carried within the IP datagrams, which require the source and destination IP addresses in the header. Without this, it would have been impossible to ping across a router. Therefore, if the user does not know the IP address, the name resolver on the local host system has to look it up, for example, via the domain name system or in the host file. The IP datagram in turn is transported by means of a network interface layer frame, for example, Ethernet, which requires in its header the MAC addresses of the source and destination nodes on the local network. If this is not found in the ARP cache, the ARP protocol is invoked in order to obtain the MAC address. The result of this action, that is, the mapping of MAC address against IP address, is then stored in the ARP cache. The easiest way to get an overall impression of this process is to capture the events described here by means of a protocol analyzer. If the IP address is known, the following format can be used. Ping IP address, for example, ping 192.168.1.71, ping 192.168.1.255 will cause all hosts on network 192.168.1.0 to respond and will cause unnecessary traffic. If the IP address is unknown, one of the following ways can be used to define the target machine. Ping hostname. This can be done provided computer's IP address has already been resolved by NetBIOS. Traceroute. In this video, we are going to see about Traceroute. A traceroute, in the simplest terms, is a way to see how information travels from one computer to another. Usually, information sent from one computer does not reach the destination computer in a single jump. In fact, it usually requires several computers to transmit the information. A traceroute identifies each computer on that list and the amount of time it takes to get from one computer to another. If there is an interruption in the transfer of data, the traceroute will show where the problem occurred in the chain. Each computer on the traceroute is identified by its IP address, which is a 9-digit number separated by periods. Working of traceroute. When you enter the traceroute command, the utility initiates the sending of a packet using the Internet Control Message Protocol or ICMP. Included in the packet is a time limit value known as the time to live, that is TTL, that is designed to be exceeded by the first router that receives it, which will return a time exceeded message. This enables Traceroute to determine the time required for the hop to the first router. Increasing the time limit value, it resends the packet so that it will reach the second router in the path to the destination, which returns another time exceeded message and so forth. Traceroute determines when the packet has reached the destination by including a port number that is outside the normal range. When it is received, a port unreachable message is returned, enabling Traceroute to measure the time length of the final hop. As the trace routing progresses, the records are displayed for hop by hop. Actually, each hop is measured 3 times. If you see an asterisk, this indicates a hop that exceeded some limit. Example of traceroute for www.google.com. Buffer overflow. In this video, we are going to see about buffer overflow. Buffer overflow attacks are the most common type of application attack. Basically, a buffer overflow attack involves overwriting memory of an application stack to execute code on its system to gain administrative access or to crash the application or operating system itself. In other words, the attacker can insert code into memory that the original application was not allocated by the operating system. Poor programming practices by application and operating system programmers open the door to buffer overflow attacks. An attacker implements a buffer overflow by typically sending the hallowing kinds of data to the application or operating system process, control sequences, large amounts of data, or incorrectly formatted data. Buffer overflow attacks involve one of the following 2 types: local exploit, remote exploit. Local exploit. This attack requires the attacker to gain initial access to the computer, typically via an email virus, Trojan horse attack, and then uses a privilege escalation attack once the computer has been compromised. Remote exploit. This attack does not require the attacker to gain initial access to the computer, but attacks the operating system or application directly across the network. Of the 2 types of buffer overflow attacks, the remote exploit attack is more dangerous since the attacker does not need initial access to the victim. The solution in preventing buffer overflow attacks is to have HIPS software on the computer, monitor the memory usage of applications and processes running in memory. If an application or process attempts to gain access to memory that was not allocated to it, the HIPS software should intercede and prevent the buffer overflow condition. IP spoofing. In this video, we are going to see about IP spoofing. IP spoofing is an attack technique that endeavors to modify the source address information in IP packet data to circumvent host or network access control or mask the source of an attack, for example, in firewall or host log data. Though the term IP spoofing generally implies the manipulation of source address information in packets, an IP spoofing attack could also involve the modification of destination address data, IP identification numbers, header length fields, packet fragmentation options, time to lives TTLs, protocol values, and source route options. This is because IP spoofing is a subset of a range of application and network attacks such as DNS and HTTP spoofing hacks that spoof IP and application data to affect an application or network exploit, denial of service, or reconnaissance gathering. Examples of attacks that utilize IP spoofing techniques include the following. Man-in-the-middle attacks, in which a hacker intercepts and captures traffic between two communication systems. Session hijacking attacks, in which a hacker is able to hijack or take over an active session between two communicating systems. Source routing attacks, in which a hacker spoofs an IP address and sets source route options in IP packets to route packets in and out of a network and past network access controls. Denial of service attacks, which utilize IP spoofing to ensure that packet responses flood a target network as opposed to the originating system, that is, the attacker's system. Trust relationship exploitation, in which a hacker is able to spoof a source IP address to circumvent IP-based operating system or application access control such as in the Unix or commands. IP spoofing attacks fall into one of the two categories: non-blind spoofing. This type of attacks takes place when the attacker is on the same subnet as the victim. The attacker sniffs the sequence and acknowledgement numbers to eliminate the potential difficulty of calculating them accurately. The biggest threat of spoofing in this instance would be session hijacking. The attacker corrupts the data stream of an established connection and then re-establishes the data stream with the attack machine using the correct sequence and acknowledgement numbers. Using this technique, an attacker could effectively bypass any authentication measures taken place to build the connection. A non-blind spoofing attack requires the use of a network packet sniffer. Blind spoofing. This type of attack is a more sophisticated attack because the sequence and acknowledgement numbers are unreachable. To circumvent this issue, the attacker sends several packets to the target machine to sample sequence numbers. This is a difficult task but not impossible. Blind attacks rely on routing and transport protocols to compromise the target. TCP Session Hijacking. In this video, we are going to see about TCP Session Hijacking. Session hijacking takes advantage of the fact that most communications are protected by providing credentials at session setup. In the TCP session hijacking attack, the attacker spoofs the victim's IP address, determines the correct sequence number that is expected by the target, and then performs a DOS attack on the victim. Thus, the attacker impersonates the victim node and continues the session with the target. The TCP axe storm problem, illustrated in figure 6.18, could be created when an attacker launches a TCP session hijacking attack. The attacker sends injected session data, and node A will acknowledge the receipt of the data by sending an ACK packet to the node B. This packet will not contain a sequence number that node B is expecting, so when node B receives this packet, it will try to resynchronize the TCP session with node A by sending it an ACK packet with sequence number that is expecting. The cycle goes on, and the ACK packets passing back and forth create an ACK storm. Hijacking a session over UDP is same as over TCP, except that UDP attackers do not have to worry about the overhead of managing sequence numbers and other TCP mechanisms. Since UDP is connectionless, edging into a session without being detected is much easier than the TCP session attacks. Sequence guessing. In this video, we are going to see about sequence guessing. This type of attack enables a flow of attack data to infiltrate the target network. The technique hinges on the fact that connections over the internet are numbered in a semi-random increasing number sequence. The attacker intercepts the current connection to the target computer and, using the appropriate software, guesses the number of the next possible sequence. If the attacker guesses correctly, a new connection to the target computer is established and malicious data or instructions can then be transmitted. As with most infrastructure attacks, a TCP sequence attacks can be thwarted by a correctly configured network firewall, which should identify any attempts to guessing a connection sequence. Network scanning and ICMP scan. In this video, we are going to see about network scanning and ICMP scan. Network scanning. Network scanners run a function called a port scanner, which uses a feature of ICMP, part of TCP IP, in order to identify hosts available in a specified network address range. The port scanner then scans identified systems for open network ports and associated services. Some network scanners use interference and other techniques to make intelligent guesses about the operating systems being run on open systems. These inferences are based on the combinations of active ports observed on a specific host. For example, if port 80 is open on a given host, it is likely running a web server. Some scanners listen to ports for traffic that provides additional information about the system connected to that port. One example of this type of surveillance is called banner grabbing and can provide a great deal of detail about the connected system. The scanner collects information that is routinely sent to any process on connection. This banner often includes details of the name and version of the application. ICMP scan. ICMP scanner is a bulk scanner that sends type 8, 13, 15 and 17 messages derived from Nmap. The tool is very useful in that it can process inbound responses by placing the network interface into promiscuous mode, thereby identifying internal IP addresses and machines that respond from probes sent to subnet network and broadcast addresses. ICMP scan being run against an internal network block. Because ICMP is a connectionless protocol, the best practice is to resend each probe using -R1 and set the timeout to 500 milliseconds using -T500. We can also set the tool to listen in promiscuous mode for unsolicited responses using the -C flag. TCP sweeps and basic port scans. In this video, we are going to see about TCP sweeps and basic port scans. TCP sweeps. Configure the device to detect and prevent TCP sweep attack. In a TCP sweep attack, an attacker sends TCP SYN packets to the target device as part of the TCP handshake. If the device responds to those packets, the attacker gets an indication that a port in the target device is open, which makes the port vulnerable to attack. If a remote host sends TCP packets to 10 addresses in 0.005 seconds, that is 5000 microseconds, then the device flags this as a TCP sweep attack. Basic port scans. Port scanning is the name for the technique used to identify open ports and services available on a network host. It is sometimes utilized by security technicians to audit computers for vulnerabilities. However, it is also used by hackers to target victims. It can be used to send requests to connect to the targeted computers and then keep track of the ports which appear to be opened or those that respond to the request. There are different levels of port scanning, ranging from light port scanning to a heavy port scan. Basic port scan. TCP connect. strobe scan, stealth scan, ACK scanning, UDP scanning, basic port scan. This is the easiest type of port scanning, which involves scanning a designated port by sending a specifically configured packet that contains a port number of the port that is to be scanned. This technique is used to determine which port is available within a specific machine. TCP Connect. A TCP Connect is used to scan a series of ports on a machine to determine port availability. If a port on the machine is listening, then the TCP Connect is successful in reaching that specific port. Strobe scan. This type of scan is generally used by a hacker to find the ports that the hacker already knows how to exploit. A strobe scan performs scanning on a more constricted level and also allows for disclosure of the username of the TCP connection. Stealth scan. This type of scan is specifically designed for hacking because it is set up to go undetected by network auditing tools. When a port scanner is used, the ports that are listening will log an error message if an inbound connection is detected, but there is no data associated with a connection. Stealth scans are able to bypass this process and therefore go undetected during audits. ACK scanning. ACK scanning is one of the more unusual scan types as it does not exactly determine whether the port is open or closed, but whether the port is filtered or unfiltered. UDP scanning. UDP scanning is also possible, although there are technical challenges. UDP is a connectionless protocol, so there is no equivalent to a TCP send packet. However, if a UDP packet is sent to a port that is not open, the system will respond with an ICMP port unreachable message. Most UDP port scanners use this scanning method and use the absence of a response to infer that a port is open. Internet Protocol Security (IPsec). In this video, we are going to see about Internet Protocol Security (IPsec). IPsec. IPsec protects IP datagrams by defining a method of specifying the traffic to protect, how the traffic is to be protected, and to whom the traffic is sent. IPsec can protect packets between hosts, between network security gateways. IPsec is not a single protocol, but rather a set of services and protocols that provide a complete security solution for an IP network. These services and protocols combine to provide various types of protection. Since IPsec works at the IP layer, it can provide these protections for any higher layer TCP/IP application or protocol without the need for additional security methods, which is a major strength. Some of the kinds of protection services offered by IPsec include the following: encryption of user data for privacy, authentication of the integrity of a message to ensure that it is not changed en route, protection against certain types of security attacks such as replay attacks, the ability for devices to negotiate the security algorithms and keys required to meet their security needs, 2 security modes, tunnel and transport to meet different network needs. IPsec enables the following features: data confidentiality. The IPsec sender can encrypt packets before transmitting them across a network. Data integrity. The IPsec receiver can authenticate packets sent by the IPsec sender to ensure that the data has not been altered during transmission. Data origin authentication. The IPsec receiver can authenticate the source of the IPsec packet sent. This service is dependent upon the data integrity service. Anti-replay. The IPsec receiver can detect and reject replayed packets. IPsec authentication header. In this video, we are going to see about IPsec authentication header. Authentication header AH provides authentication and integrity to the datagrams passed between two systems. It achieves this by applying a keyed one-way hash function to the datagram to create a message digest. If any part of the datagram is changed during transit, it will be detected by the receiver when it performs the same one-way hash function on the datagram and compares the value of the message digest that the sender has supplied. The one-way hash also involves the use of a secret shared between the two systems, which means that authenticity can be guaranteed. AH can also enforce anti-replay protection by requiring that a receiving host sets a replay bit in the header to indicate that the packet has been seen. Without this protection, an attacker might be able to resend the same packet many times. For example, to send a packet that contains withdraw $1,000 from account X, the two routers confirms that the data between them is sent in clear text. The AH function is supplied to the entire datagram except for any mutable IP header fields that change in transit, for example, time to live TTL fields that are modified by the routers along the transmission path. AH works as follows. The IP header and data payload is hashed. The hash is used to build a new AH header which is appended to the original packet. The new packet is transmitted to the IPsec peer router. The peer router hashes the IP header and data payload, extracts the transmitted hash from the AH header and compares the two hashes. The hashes must match exactly. Even if one bit is changed in the transmitted packet, the hash output on the received packet will change and the AH header will not match. Encapsulating Security Payload ESP. In this video, we are going to see about Encapsulating Security Payload ESP. Encapsulating Security Payload ESP is a security protocol used to provide confidentiality, that is encryption, data origin authentication, integrity, optional anti-replay service, and limited traffic flow confidentiality by defeating traffic flow analysis. ESP provides confidentiality by performing encryption at the IP packet layer. It supports a variety of symmetric encryption algorithms. The default algorithm for IPsec is 56-bit DES. This cipher must be implemented to guarantee interoperability among IPsec products. All encryption algorithms used with ESP must operate in cipher blockchaining CBC mode. CBC requires that the amount of data to encrypt be a multiple of the block size of the cipher. This requirement is met by adding padding to the end of the data when necessary to encrypt. Ciphers in CBC mode also require an initialization vector IV to jumpstart the encryption process. This IV is contained in the payload field generally as the first bytes, although it is up to a specific algorithm specification to define where it obtains its IV and a size of the IV. For instance, when using triple DES CBC, the IV is the first 8 bytes of the protected data field. ESP is both a header and a trailer. It encapsulates the data it protects. The header portion contains the SPI and sequence number. The trailer contains the padding, if any, an indicator regarding the length of the pad, the next protocol of the data after ESP, and the authentication data. Internet Key Exchange. In this video, we are going to see about Internet Key Exchange. The Internet Key Exchange IKE is an IPsec, that is Internet Protocol Security Standard Protocol, used to ensure security for virtual private network VPN negotiation and remote host or network access, specified in IETF request. The purpose of IKE is to allow devices to exchange information that is required for secured communication. This includes cryptographic keys that are used for encoding authentication information and performing payload encryption. IKE works by allowing IPsec-capable devices to exchange SAS which populate their SADs. These SADs are then used for the actual exchange of secured datagrams with the AH and ESP protocols. IKE is considered a hybrid protocol because it combines and supplements the functions of three other protocols. The first of these is the Internet Security Association and Key Management Protocol (ISA-KMP). This protocol provides a framework for exchanging encryption keys and security association information. It operates by allowing security associations to be negotiated through a series of phases. ISA-KMP is a generic protocol that supports many different key exchange methods. In IKE, the ISA-KMP framework is used as the basis for a specific key exchange method that combines features from two key exchange protocols. OAKLEY describes a specific mechanism for exchanging keys through the definition of various key exchange modes. SKEME scheme describes a different key exchange mechanism than OAKLEY. IKE uses some features from SKEME, including its method of public key encryption, its fast rekeying features. Internet Key Exchange Operation. IKE does not strictly implement either OAKLEY or SKEME, but takes bits of each to form its own method of using ISA-KMP. Because IKE functions within the framework of ISA-KMP, its operation is based on the ISA-KMP phased negotiation process. There are two phases as follows: ISA-KMP Phase 1, ISA-KMP Phase 2. ISA-KMP Phase 1. The first phase is a setup stage where two devices agree on how to exchange further information securely. This negotiation between the two units creates an SA for ISA-KMP itself and ISA-KMP SA. The security association is then used for securely exchanging more detailed information in Phase 2. ISA-KMP Phase 2. In this phase, the ISA-KMP SA established in Phase 1 is used to create SAs for other security protocols. Normally, this is where the parameters for the real SAs for the AH and ESP protocols would be negotiated. The ISA-KMP SA negotiated during Phase 1 includes the negotiation of the following attributes used for subsequent negotiations: an encryption algorithm such as the Data Encryption Standard DES, a hash algorithm MD5 or SHA as used by AH or ESP, an authentication method such as authentication using previously shared keys, a Diffie-Hellman group. Security Association SA. In this video, we are going to see about Security Association SA. IPsec introduces the concept of the Security Association SA. An SA is a logical connection between two devices transferring data. An SA provides data protection for unidirectional traffic by using the defined IPsec protocols. An IPsec tunnel typically consists of two unidirectional SAs which together provide a protected full duplex data channel. The SAs allow an enterprise to control exactly what resources may communicate securely according to security policy. To do this, an enterprise can set up multiple SAs to enable multiple secure VPNs as well as define SAs within the VPN to support different departments and business partners. Security Association Mode. SAs operate using modes. A mode is the method in which the IPsec protocol is applied to the packet. IPsec can be used in tunnel mode or transport mode. Typically, the tunnel mode is used for gateway-to-gateway IPsec tunnel protection, but transport mode is used for host-to-host IPsec tunnel protection. A gateway is a device that monitors and manages incoming and outgoing network traffic and routes the traffic accordingly. A host is a device that sends and receives network traffic. Transport mode. The transport mode IPsec implementation encapsulates only the packet's payload. The IP header is not changed. After the packet is processed with IPsec, the new IP packet contains the old IP header with the source and destination IP addresses unchanged and the processed packet payload. Transport mode does not shield the information in the IP header. Therefore, an attacker can learn where the packet is coming from. Tunnel mode. The tunnel mode IPsec implementation encapsulates the entire IP packet. The entire packet becomes the payload of the packet that is processed with IPsec. A new IP header is created that contains the two IPsec gateway addresses. Tunnel mode ESP prevents an attacker from analyzing the data and deciphering it, as well as knowing who the packet is from and where it is going. Virtual Private Network (VPN). In this video, we are going to see about Virtual Private Network (VPN). A virtual private network (VPN) is a network technology that creates a secure network connection over a public network such as the Internet or a private network owned by a service provider. Virtual private networks are point-to-point connections across a private or public network such as the Internet. A VPN client uses special TCP IP-based protocols called tunneling protocols to make a virtual call to a virtual port on a VPN server. In a typical VPN deployment, a client initiates a virtual point-to-point connection to a remote access server over the Internet. The remote access server answers the call, authenticates the caller, and transfers data between the VPN client and the organization's private network. To emulate a point-to-point link, data is encapsulated or wrapped with a header. The header provides routing information that enables the data to traverse the shared or public network to reach its endpoint. To emulate a private link, the data being sent is encrypted for confidentiality. Packets that are intercepted on the shared or public network are indecipherable without the encryption keys. The link in which the private data is encapsulated and encrypted is known as a VPN connection. There are two types of VPN connections: remote access VPN, site-to-site VPN. Remote access VPN. Remote access VPN connections enable users working at home to access a server on a private network using the infrastructure provided by a public network such as the Internet. From the user's perspective, the VPN is a point-to-point connection between the computer, that is the VPN client, and an organization's server. The exact infrastructure of the shared or public network is irrelevant because it appears logically as if the data is sent over a dedicated private link. Site-to-site VPN. Site-to-site VPN connections, also known as router-to-router VPN connections, enable organizations to have routed connections between separate offices or with other organizations over a public network while helping to maintain secure communications. A routed VPN connection across the Internet logically operates as a dedicated WAN link. When networks are connected over the Internet, a router forwards packets to another router across a VPN connection. To the routers, the VPN connection operates as a data link layer link. A VPN is an inexpensive, effective way of building a private network. The use of the internet as the main communications channel between sites is a cost-effective alternative to expensive leased private lines. The relative ease, speed, and flexibility of VPN provisioning in comparison to leased lines makes VPNs an ideal choice for corporations who require flexibility. Disadvantages: the lack of quality of service QoS management over the internet can cause packet loss and other performance issues. Adverse network conditions that occur outside of the private network is beyond the control of the VPN administrator. Vendor interoperability is another potential disadvantage, as VPN technologies from one vendor may not be compatible with VPN technologies from another vendor. Point-to-point tunneling protocol (PPTP). In this video, we are going to see about point-to-point tunneling protocol (PPTP). Point-to-point tunneling protocol (PPTP) is a protocol that is a set of communication rules that allows corporations to extend their own corporate network through private tunnels over the public internet. PPTP encapsulates point-to-point protocol (PPP) frames in IP datagrams for transmission over the network. PPTP can be used for remote access and site-to-site VPN connections. PPTP uses a TCP connection for tunnel management and a modified version of generic routing encapsulation (GRE) to encapsulate PPP frames for tunneled data. The payloads of the encapsulated PPP frames can be encrypted, compressed, or both. When using the internet as the public network for VPN, the PPTP server is a PPTP-enabled VPN server with one interface on the internet and a second interface on the intranet. Layer 2 Tunneling Protocol (L2TP). In this video, we are going to see about Layer 2 Tunneling Protocol (L2TP). Layer 2 Tunneling Protocol (L2TP) is an extension of the point-to-point tunneling protocol (PPTP) used by an Internet Service Provider (ISP) to enable the operation of a virtual private network (VPN) over the Internet. L2TP allows multi-protocol traffic to be encrypted and then sent over any medium that supports point-to-point datagram delivery, such as IP, X.25, frame relay, or asynchronous transfer mode. L2TP is a combination of PPTP and Layer 2 forwarding, that is L2F. L2TP represents the best features of PPTP and L2F. L2TP encapsulates PPP frames to be sent over IP, X.25, frame relay, or ATM networks. When configured to use IP as its datagram transport, L2TP can be used as a tunneling protocol over the Internet. L2TP also uses UDP to send L2TP encapsulated PPP frames as tunneled data. The payloads of encapsulated PPP frames can be encrypted, compressed, or both, although the Microsoft implementation of L2TP does not use MPPE to encrypt the PPP payload. Advantages of L2TP includes: high data security is provided for critical applications. It is reliable, scalable, fast, and flexible. It provides excellent and efficient connectivity. It is cost-effective and does not have overhead cost after implementation. Disadvantages of L2TP include: the main disadvantage in using L2TP is the amount of configuration needed for setup is high. With some firewalls, the L2TP is at a disadvantage as it encapsulates the data twice, which can affect the speed of a transmission.